Okay. Okay, so let's continue with our geometric approach to stoichiometry. I hope that everything is quite straightforward. Hopefully, oops. And well, we've defined this special matrix here. I'll give you a more sort of rigorous definition later on, but it's essentially, well, in this particular case, it was a 2x4 matrix, essentially because you had two elements, hydrogen and oxygen. So all the rows, okay, of this special matrix refer to atoms, okay, elemental species, in the ordering that you've decided, okay? So in this case, H is first and O is second. And then clearly the columns refer to the ordering of the species, okay? And this is essentially how many atoms in each species, okay? Now, we have said that essentially this matrix, okay, applied to a composition vector will give us the elemental composition. So in particular, if I'm interested in the elemental composition, okay, so a vector which gives me the number of moles, in this case of hydrogen and oxygen, okay. So you see it's a 2x1 vector. All I have to do is apply the matrix A, okay, to the vector n, okay, where essentially, well, matrix A is matrix A, okay, over here, and vector n is our usual vector of composition. So it has components, number of moles of H2, number of moles of O2, number of moles of H2O, and number of moles, for example, of OH, okay? Now, clearly, the elemental composition has to remain constant, as we know, okay? And so it's essentially equal to the elemental composition that you had at the beginning. So the initial elemental composition, okay? Let's write it here, initial elemental composition, okay? So clearly, rewriting what we just said, so the elemental composition is A applied to the composition vector is equal to the initial elemental composition, okay? So if we differentiate, dne is equal to, well, A is a constant matrix times dn, okay, is equal to what? Well, to the differential of a constant, which is obviously 0, okay? So we have exactly what we said yesterday, okay? In order for your elements or atoms to be conserved, okay, you cannot move along any direction in the phase space, okay? But essentially, the infinitesimal change, okay, in composition has to follow a certain constraint, a certain direction, and this is your constraint, okay? The constraint is that the vector, okay, dn, okay, must be such that if matrix A is multiplied by it, okay, it's multiplied by the vector of the composition vector. In this case, it's a differential relationship, but it doesn't really matter. This must be equal to 0, okay? So what this tells us is that dn cannot be chosen at random, arbitrarily, okay? Within your phase space, but it is subject to this constraint. Now, by definition, okay, if given a matrix A, you have that A times dn is equal to 0, then we say that the vector dn, okay, does not belong to generically, to Rn, but it actually belongs to a subspace of Rn, which is called the kernel of A. Okay, you probably have seen this in linear algebra. It's also called the null space of A. Okay, and what is this? Well, it's a subset. Okay, you can say this. It's a subset of Rn. So it's just a little smaller. Okay. For example, in 3D, it could be a plane. Okay. We saw, for example, in 3D, the conservation of atoms was a line. Okay, a direction, the stoichiometric vector. Okay, so that's what the kernel of A essentially is. Okay. Let's be more specific. Kernel of A is essentially a vector space, okay, which has dimensions are ns minus ne. Okay, remember, this is the number of species. In our case, it was 4. And this is the number of atoms or elemental species, and it was 2. So in our example of the hydrogen and oxygen, the kernel of A, okay, let me see if I am recording, yes. The kernel of A is R2, okay? So what does that mean? Well, it's a plane in R3. Do you get it? So what does it mean when, okay, most of you will know this, but I'll repeat this. What does it mean when a vector space like the kernel of A, okay, has dimensions R2, as dimensions 2, for example, ns minus ne, okay? It means that the basis that generates it, of basis vectors that generates it, is composed of ns minus ne basis vectors. Okay, in this case, only 2. Okay, so it's a plane, it's generated by 2 basis vectors, obviously. Okay, or another way of saying this is kernel of A is, in English, we say spanned, or if you will, generated, okay, by ns minus ne basis vectors. Okay, and we will call this basis of this subspace kernel of A, we will call it Nikkei. Okay, no wonder. So these are vectors, still, okay, they still have ns components, so they still belong to ns, okay? But their number is, okay, equal to ns minus ne, okay? So I will essentially be sticking to the example later on that we've always had. So in the case of 4 species, okay, and 2 elements, hydrogen and oxygen, you only have 2 basis vectors, okay, because it's 4 minus 2, okay, so you have 2 basis vectors, okay. Did I say 4? It's 2 basis vectors, so it's 4 minus 2, okay, 4 species minus 2 atomic elements, okay. So you live in R4, okay, but there is a restriction, okay, on where you can move in R4, okay? And that is, in fact, the kernel of A. And the kernel of A is generated by two basis vectors. So it's a plane, okay? It's a plane in a four-dimensional space, okay? So again, let's remember what we said over here, okay, as a definition. Because a dn is equal to 0, it means essentially that these special vectors lie in the kernel of A. Okay, so dn cannot be any vector, but it has to lie in this kernel of A. So if dn is in the kernel of A, then how do we express this? As a linear combination of the basis vectors of the kernel of A, right? So dn can be expressed very simply as the basis vectors, okay, times some component. Well, obviously this is an infinitesimal, so we're going to just write the component like this. Now, where does k go to? Well, from 1 clearly to ns minus ne, because that's the amount of the number of basis vectors that you have. Okay, if you integrate this, okay, basically what you have is n minus n0, so the current composition minus the initial composition, equal to simply the sum of Nikkei, and then what we can say here is psi minus psi 0. Okay, usually this psi 0, if this is clearly the progress variable, then we know that it's 0, but it doesn't really matter. Okay, so essentially your composition can be expressed as the initial composition, okay, plus a linear combination of your basis vectors of the kernel of A, okay? So let me draw a very confusing diagram now, very crooked diagram, okay? So again, I will always use R3 now clearly, because I mean that's all I can use. So this is your original phase space. If you're actually living in R4, it will be a projection, okay, in 3 dimensions, clearly, because that's all we can represent, obviously. Okay. Now, what does this say? It says that your composition, okay, will be, well, first of all, your initial composition. So we're giving the system an initial composition. We are adding a certain number of moles of each species in your container, for example. So what we're doing in effect is we're adding atoms, okay, that we need to conserve, okay? And that is N0, okay? N0. Then, having added N0, we can only move, okay, in this restriction, okay, in this space, okay, spanned by the basis vectors. Now, in the case of hydrogen and oxygen, for example, we have 2, right? We said we have only 2 because it's 4 species minus 2 atoms. So what we can do is we can represent these basis vectors, one going like, for example, in this direction, the other one going, for example, in this direction here. So this would be N1, okay? This other would be N2, okay? And then I hope you can see it, but this generates, okay, a plane, okay? Now, all we can do is move it within this plane here, okay? So n minus n0 belongs to the kernel of A. So the kernel of A is this plane here, okay? And, well, that would be N, okay? And this is clearly N minus N0, okay? Which lies, as we said, in the kernel of A, okay? So, long story short, we have restricted, okay, your phase space in a subspace, which is your stoichiometric, you can call it stoichiometric manifold, okay? Essentially, it's a subspace that you can move around in, okay? And you know that by staying on this manifold, you're always conserving atoms, okay? Which is pretty nice, okay? Let's write down a few other things. Is this clear as a representation, or, I mean, I'm just constructing some sort of rigorous, not rigorous, but I mean, some more rigorous sort of linear algebra kind of approach to stoichiometry, okay? Now, clearly, I haven't told you how I can find the basis vectors, Ni1 and Ni2, okay? Well, if you have MATLAB or Mathematica, you can write down, for example, the matrix A for any chemical system, and then type the command null space of A, okay? And it will give you the set of NS minus NE basis vectors, okay? If you don't have MATLAB or Mathematica, we have to, well, use paper and pencil. And there is a trick, okay? There is a very straightforward procedure that I won't anticipate now. I'll do it later. Let me just say that you probably have realized by now that Ni1 and Ni2, okay, are representative of each independent atom preserving reaction that you can have in your system, okay? And I will prove it to you right now. Let me just write down again this relation here, just to prove that. So N minus N0 is essentially linear combination of the new K's, okay? Now, clearly, if I apply the matrix A to this, okay, well, you see that matrix A multiplies now the Ni's here, and this is by definition 0, right? I hope you agree, because Ni is a basis of the kernel of A, and by definition, therefore, A Ni is 0, okay? So this proves, in some sense, that N minus N0, okay, is also in the kernel of A, okay, because A times N minus N0 is 0, okay? And it also tells me that a very simple way that we've seen before of writing the conservation of atoms is simply writing AN equals AN0, okay? Which, by the way, will be equal to the initial number of moles of the initial elemental composition, okay? Now, let me just go a little bit forward in this representation, because now, suppose I give you, okay, my chemical system. So, for example, H2, O2, H2O, and OH, 4 species, okay? Well, I can write down right away, once I've ordered my species and my elements, I can write down matrix A, okay? Now, given matrix A, I can determine somehow, okay, the basis vectors of my kernel of A. So my stoichiometric manifold, okay? What I'm doing is I'm determining the basis vectors of the kernel of A, and each basis vector is in fact a stoichiometric coefficient representing an independent reaction. And I'll prove this to you later on. Now, suppose now that I've determined all of the independent reactions, I know the subspace. How do I determine my, how do I determine the equilibrium point? Okay, I'm just repeating what I kind of said a little bit less rigorously the other day. Okay, so I have this manifold here somehow, okay, that I know. Okay, this is the basis vector, ni2. This is the other basis vector. Well, you can write it better. Oops, no, this is 1. Okay. Now, I know the subspace, okay? Now, all I have to do, okay, well, this is one reaction, right? And this is the other reaction. So, in fact, what I can do here, I can represent, okay, an abscissa which describes the progress variable here along this reaction, and another progress variable here along the other reaction, right? So these are just two scalars that tells me how far to the right and how far to the left these two independent reactions are. And now, if I can write down a function which represents my Gibbs energy as a function of, for example, psi1 and psi2, okay, suppose is something like this. I'm just giving you some levels, okay? So this is a function, say in a two-dimensional space. It's like a level set plot, okay? Where this is my my minimum. Well, then this will be my equilibrium point. I hope you can see this. So this would be psi of 1 of equilibrium, okay? And this will be the value psi 2 of equilibrium, okay? So the point now is, well, how do I represent this, okay? And this is what we're going to do next, okay? But I hope this is clear. We had done this in along one direction, maybe yesterday it was. Now we're just simply generalizing into multi-dimensions, okay? Let's go back to our hydrogen and oxygen system so that it's probably going to be clear what we're doing, right? So we have, well, NS is equal to 4, okay? So let's see what species we have. Well, we have H2, O2, H2O, and OH, right? So this is the numbering, 1, 2, 3, 4, in terms of species, right? Now, clearly the elements are 2, hydrogen and oxygen. We can number them again, 1, okay, for hydrogen and oxygen, okay? So we construct now our matrix, which is really easy to do. A. It will be a 2x4 matrix, 2 rows representing the elemental species and 4 columns representing the molecular species. So we just look at H now to fill in the first row and ask ourselves how many H atoms in the first species? 2, 0, 2, 1, okay? And then for oxygen, we do exactly the same, okay? 0, 2, 1, 1, okay? That's our matrix A. Now, At this point, we would have to establish the basis vectors of the kernel of A, okay? So how many do we have? Well, we have Ni1 and Ni2, right? Because, so this is a basis of the kernel of A, okay? Now, we said that a reaction is a vector in the phase space, okay? Clearly, a reaction that conserves atoms, as we said, is a basis of the kernel of A, because clearly we proved that, we said that. Let's do the opposite. Let's see essentially if a known reaction, since I'm not going to be telling you how to determine numerically Ni1 and Ni2, but we know one of the reactions that preserves atoms, right? We just wrote it many times. It's this one. It's pretty simple. Okay. So we know that we're pretty sure that by looking at this conserves atoms. Okay. There's 2 atoms of hydrogen here, 2 atoms of hydrogen here, 1 of oxygen and 1 of oxygen. Okay. Now, we also know that the definition of progress variable, let me write it again, is something like this. Okay. It's not very nicely written. There you go. That's the progress variable, right? So every number of moles, the composition of the ith species, okay, is equal to N0 plus, sorry, this is scalar. Don't write down the vector. Sorry, that was my mistake. Is equal to, again, the difference in stoichiometric coefficients, okay, times the progress variable, okay? So vectorially, the composition, okay, vector is equal to N0 plus the components here can be contained in a vector, okay, times the scalar, which is the progress variable, okay? In this particular case, okay, Ni, which has components as the difference of the stoichiometric coefficients, well, to know what kind of vector it is, how do we write it? Well, we take the first species, okay, which is hydrogen, and we see, well, what's the stoichiometric coefficient on the right side? It's 0, okay, the Ni double prime, minus 1, okay, Ni prime. For oxygen, it's still 0, and then on the right side and on the reactant side is a half, so it's minus a half. For water is 1 minus 0. And in fact, for OH, it doesn't appear here, so it's just simply 0 minus 0. Okay? So again, it's something like minus 1, minus a half, 1, 0. Okay, that's our stoichiometric vector. Now, this is one of the vectors which compose the basis, okay, of the kernel of A. Well, we can prove quite easily by just verifying that A times, okay, applied to Ni is equal to 0. Is it? all you have to do is take A, zero, 2, 1, 1, okay? And multiply it by this vector here. -1, -0.5, 1, 0, okay? And, well, I hope you can see it, but this is pretty much the 0, 0 vector, okay? And so we have proved that Ni belongs to the kernel of A, okay? Now, obviously, the way to proceed is not clearly that of writing down the independent reaction, clearly, because we don't know those. Imagine a system of, I don't know, 25 species and 4 elemental species, okay? This is typically the case of hydrocarbons, okay, where you have a lot of species. Well, the fuel and oxygen, of course, but you may have nitrogen for air and all the intermediate or radical species, CO2 as well as water, and et cetera, et cetera. So in fact, for very simple hydrocarbons such as methane, very simple kinetic systems or chemical systems that can well reproduce the chemistry of methane, well, you have more than 50 species, in fact. And, well, so this matrix A, and usually the number of atoms is much smaller, obviously, because you have carbon, atom, hydrogen, atom, oxygen, and possibly nitrogen. So essentially 4, okay? So matrix A would be essentially a 4 by 50 huge matrix, okay? And the number of basis vectors, okay, is 50 minus 4, okay? The basis vectors of the kernel of this matrix. And so you would have, what, 46 basis vectors. Now, that means that you have essentially 46 ways in which you can react all of these species so that essentially the atoms are conserved, okay? And of course, you can't just figure them out. You can't just sort of try them out, okay? You would have to build, well, an automatic procedure, okay, or a mathematical procedure, so that given the matrix A, we can calculate the basis vectors, okay, the 46 basis vectors, and if we know the basis vectors, okay, I hope you can see this. If you know one of the basis vectors, for example, in this case, it's this guy here, okay, so one of those Ni vectors, then you see that you can construct the reaction right away. Why? Well, look at the components, okay? The components are Ni double prime minus Ni prime. And the ordering of the species is the one you gave. So the first one is hydrogen, oxygen, then water, and OH. So to actually rewrite the reaction, okay, that conserves the atom, well, you take hydrogen. The minus sign means essentially that, you see, there is a 0 minus, okay? So essentially, there is no hydrogen on the right side. So the hydrogen is clearly over in the reactants, okay, with a 1, okay, multiplying it. Oxygen is the same. It's in the reactant side because there's a minus with a 1/2, okay, stoichiometric coefficient. And then for water, you see there's a plus sign here, meaning that it's on the product side, okay? So it's on the right side. Again, because the components are right side minus left side. Okay, the product side minus the reactant side. Okay, so I hope that is clear. So in this case, we cheated. Okay, I told you the reaction first, and then I verified that this reaction is really corresponds to a basis vector, a stoichiometric vector, which is a basis vector of the kernel of A. Okay, so I cheated. We should do the other way around later on. The last thing that we're left to do, in fact, is the following. Let me just redraw the. Let's see if I can do it in 10 minutes. Let me redraw, okay, the overall scheme, okay, which is essentially my phase space, and then the kernel of A, which is our subspace that conserves the atoms, okay? Now, each of those directions, okay, is a basis vector of the kernel of matrix A, okay? But in fact, okay, we have here an initial condition. No, we said that this is N0, right? So really, if you look at the projection here of N0 on these axes here, well, this corresponds to the progress variable equal to 0. Okay, this is by definition the progress variable. When it's 0, it means that the composition is equal to the initial composition. Okay, then essentially what can happen is that the reaction can shift more to the right. For example, here, all the way down to, for example, a value of psi r, and all the way down here to a value of psi left. So we have the leftmost and rightmost values of the progress variable. And we can do this for both the first reaction and the second reaction, okay? So that we span a whole plane, okay, where essentially the plane is identified by psi1 and psi2, okay? Any point on this plane. Now, how do we actually calculate these limits, okay? Well, it's pretty straightforward. So I'll give you just a very basic example. I think it's much better if I give you an example instead of generalizing. So suppose that I have this reaction here, okay? I'm just making it up. So it's alpha A, so alpha is the stoichiometric coefficient, A is the species, plus beta B, okay? These are the two reactants, for example. And on the product side, we have gamma C and delta D, right? And I'm interested in knowing the left and the right limits of the progress variable. Well, first of all, we can write down the definition of the progress variable. Very simply, Na minus Na0 divided by 0 minus alpha. So it's minus alpha here. So these are the two products, the two reactants. 9 out of 10, when I want to say products, I say reactants and vice versa, okay? NB minus NB0 divided by minus beta, okay? And then NC minus NC0 divided by, now it's plus gamma, because it's gamma minus 0, and ND minus ND0, okay? Is equal to, divided by delta, okay? That's my progress variable. Now, let's see how to find, for example, psi L. Well, this means that the reaction is completely shifted towards the left, okay? So we take this process here, completely shifted towards the left. Right? And when does this process end? When is it that I cannot go any further left? Well, when either C or D is completely depleted, completely zero, okay? Zero number of moles. So all we have to do, but I hope you agree with that, okay? It cannot be negative. So we take this relationship between the number of moles of C and the number of moles of D, can you hear me?
Yes, Professor.
Oh, okay. You paused a little bit, so I was very scared. Okay. And what do? We express now the what we want to understand now is which one is depleted first. Okay, which one is it? C or D? Okay, because this will tell us when to stop. Okay, when this reaction cannot go any further left. And at that point, we can define my psi left. So we take, for example, NC. You can do the opposite, but we express NC as a function of ND. So NC0 plus gamma over delta ND minus ND0 and D0, okay? And for example, now what we do is we take a graph, okay? We know that there is some initial, okay, point, which is, this is D, okay? This is ND, this is NC. That's ND. That's ND0. That's NC0. So my initial point is here. And now, well, clearly, this is well, you can see it's a straight line, right? And it's something like, for example, this. It could be, okay? Where the slope clearly is gamma over delta, okay? Now, if this line here, if this relationship here intersects this axis first, well, then this means that you see NC here is equal to 0, where ND, on the other hand, is still non-zero. So that means that NC is the so-called limiting product, okay? It will end first. Of course, depending on the values of gamma, delta, and your initial point, we could have had something like this, okay? Then in this case, D would be the limiting product, okay? So now that we know that NC, okay, finishes first, when NC is equal to 0, we know that psi has attained its leftmost or smallest value, okay? You cannot go any smaller than that because otherwise NC would be negative, okay? And so essentially we take the definition, okay? And we say that NC minus NC0 divided by gamma, when NC is 0, so 0 minus NC0 divided by gamma, that is equal to psi left, okay? So we have to figure out reaction per reaction, okay, which are the limiting products. In this case, C is the limiting product. Let me write it here, limiting and for the other value, psi r, the maximum value, we do the opposite, okay? We take well, we don't have too much time here, but we take this process here, completely shift it to the right. Okay, we can write down now the relationship between A and B. Okay, in this case, it would be alpha over beta. Okay, NB minus NB0. Okay, and it's exactly the same as before. We see for psi going all the way to the right, so towards the maximum value, we want to know essentially whether it is B or A that is depleted first. So for example, this is NB, this is NA, okay? And as it turns out, maybe it's something like this, okay? So now it's, again, it's NB that is 0. So it's B, for example, that is the limiting product. And so just to finish things, very simply, exactly like I did here, NB minus NB0 divided by minus beta, imposing the limiting product to be 0, okay, will tell me that this is the highest or the rightmost value that I'm interested in, okay? Maybe at the beginning of the next session, of the next lesson, sorry, I will give you an example, okay? This is something that you should learn a little bit and try to grasp, okay? Because it may be needed, okay, to calculate. Well, it is certainly needed to calculate as part of the calculation of the equilibrium, okay? So let me press the stop button.